got the equation. Cellular respiration. Your brain needs glucose. Absolutely. If you are deficient in glucose, if you don't take in enough glucose, if your cells don't take in enough glucose, this isn't going to happen. Because you need this for that to happen. And if you can't get that, okay, then you're going to have problems. So that's why glucose and oxygen are so important for your brain tissue. If your brain tissues aren't getting enough glucose, either from your diet or from metabolic processes, certainly if your brain is deficient in oxygen, you're not going to get enough ATP to drive this process. 70% is needed to just for this little pump, but it's super important. Okay, so it requires ATP. It pumps 3 sodium out, 2 potassium in. Okay, so why is that important? We're gonna see at the very end, but I kind of want to just give you a preview right now. Okay, if say your cell is at rest, so our gates are closed, okay, but when your neurons are at rest, this is happening. You're having potassium's going out through those leaky channels and sodium's coming in through those leaky channels. This right here helps to maintain the resting membrane potential. Because if you have too many potassium going out, then this pump is going to pump it back in to maintain that. Okay, so just think about the pump kind of actively always working in the background. The leaky channels, they're allowing ions to cross. Okay, so both of those help to maintain the resting membrane. Okay, so we sketched those 3 channels, defined them. Okay, so let's return to an action potential. So how do you get an action potential? And what's an action potential? An impulse. Okay, so let me draw that graph that I drew last time. We have, this is our graph for an action potential. On the x-axis, we have time, and it's really just in milliseconds. Okay, 1, 2, 3, 4, maybe 1, 2, 3, 4 milliseconds. Time, milliseconds. On the y-axis, we have our voltage, so we have our millivolts. Okay, so let's graph. Let's say 70, 0, 30, 1. Yeah, let's just say that. Okay, so let's say there was some kind of stimulus, okay, that causes these gated channels, what kind of voltage gated channels, to open. Okay, so let's just say it's, your exposure to sunlight. Let's just go with that. So at rest, all of the voltage gated channels are open. Okay, once a cell, neurons are cells, receives a signal from the other cell, okay, you have a series of events that are occurring from the dendrites that go through the soma, and then here, what is this part of the cell called? What is, not that, what is this little part right here at the base of the soma and the beginning of the axon? Yeah, the axon helix. So axon Okay. And then, let me just, and I didn't say this last time, chemically gated and mechanically gated transmembrane proteins, they are located in the soma and on the dendrites. Voltage gated channels are along the axon. Okay, so we're gonna focus on the voltage gated channels, all those channels here. Okay, so first thing that happens after this, well, let me draw this. What is going on, if you had to label this part right here, what would you label it as? Yes, the resting membrane potential. Okay, so at rest, before anything is happening, this is what the graph would look like. Okay, the neuron receives the signal from a previous neuron, we call it the presynaptic neuron, and this is what happens. Okay, these voltage gated channels begin to open. More specifically, these channels open. So think about what would happen to the resting membrane potential if the sodium voltage gated channels opened. What would happen? What would happen to the inside? If you get more positively charged ions flowing in, how would that change the membrane potential? Okay, let's go back to this word. If something is polar, what does that mean? What? Polar. Polar means different in charges, okay? Positive, negative, okay? If you have, I think I mentioned this, if you have a really polarized discussion with someone, that means that you have very, very different opinions, okay? Right now, this membrane is polar because the inside is more negative than the outside. By how much? -70, okay? If you start having sodium coming in through the sodium voltage gated channels, is it gonna be as polarized? No, because the inside's gonna be what? More what? More positive, okay? So let's draw on our graph. How do you get to be more positive? More positive is taking the -70 more closer to 0, okay? So it's becoming more positive. In other words, you're starting not to have as much polarization across the membranes. So this is what would happen, start to happen. And then we can label this here as sodium gates start to open. Okay, so that's what's happening. Sodium gates are opening, sodium rushing in. You're starting to have this rapid influx of sodium in. And that's just what happens. The first thing that happens after the signal reaches the axon hillock, the sodium voltage gated